Let us go ahead and get this show started today. Okay, once again, we're broadcasting remotely. We're going to go ahead and basically use the first hour to go through and work together and introduce some new examples and revisit some existing ones, really kind of talk about the assignment that's coming up and think some more about the whole idea of optimization and how we can really use Dynamo to drive optimization. So that's where we're going to go ahead and get started. We're going to take a break right around 10, for about half an hour. I'm going to go ahead and be offline, but then rejoining you around 10:30. So hopefully we'll be able to use that period from like 10 to 10:30 to, if you want to take a look at the assignment, start digging into that a little bit and see if you have any questions around that. But hopefully be able to use that time. The TAs will be available kind of in the classroom too, but we'll take a sort of extended break in the middle of class and then be joining you back again for like the last 20 minutes. So just to let you know what's kind of happening there. So in terms of getting going, let's go ahead and take a look at what we have available today. If you can, please go ahead and download off of coursework the session 12 examples. Also, if you can, please go ahead and download the assignment 3 files. In the assignment 3 folder, you'll find a couple different things there. You'll find the assignment description itself, as well as a starting point, which contains, just some of the useful nodes we've been working with, some of the different little pieces and chunks that'll actually help you get the assignment done. So maybe a good place to start is actually there, just looking at the assignment, if people haven't had a chance to dig into that yet, and just give you a sense of really what we're after. So here's the assignment, and you're basically going to have a week to work on this. We had talked about having it due next Thursday, but as I went through and completed all the steps in the assignment, I found that there's really quite a bit of interesting stuff in here, so I wanted to give you a little bit of extra time. Hopefully it'll go fairly quickly for you, but I want to give you the time to have a chance to dig into it, ask questions of the TAs. So if you can get it done this week, super, but it's going to be due next Tuesday, 10 in the evening. And the idea is as follows. Okay, so what we're going to be doing is actually looking at a linear structure, very much like that stadium we've been looking at, that parametric stadium, but really looking at it in some different forms and how we could use that same basic structure to generate a lot of different forms. Something very large scale like an airport concourse, something very small scale like a parking structure, something like that. But what we want to do is basically start by just creating a linear structure as opposed to the arc structure. Okay, put some truss components in it, grid the surface, and then do a little variation on it by kind of adding a little bit of a wave to the ends of the trusses. So going ahead and kind of introducing just a little more variation to the whole thing, as well as going ahead and considering the issue of, are the different panels, are they facing the sun? And if they are facing the sun, can we adjust them to indicate that they could actually be solar collection panels? So that's kind of the broad overview of what's going on here. And again, to get yourself started, I would highly recommend taking a look at either the second half of session 9, the first half of session 10, because really a lot of the same components and the same logic that we use to construct the parametric stadium would be appropriate here. Okay, so Raj, go ahead, try that again. I didn't hear your voice, but I saw that you were trying to talk. Or type a message. Okay, no worries. We got a little bit of a back, moving. Hopefully that's not too bad. I'm trying to think if I need to mute anything on this side. If you're in, yeah. So as Raj says, if you can't mute everyone, in fact, I can sort of mute everyone. Let me try that. Okay, everyone's muted right now. When it's time to ask a question or something like that, just jump on in and unmute yourself. Okay, super. So let's go ahead and take a look at some examples of what we have in mind and then kind of think about how you can approach this, because only completing the assignment, I actually sort of worked out some examples that are fairly similar. Let me go back over to Revit and kind of just show you how I approach the assignment. What I'll do is I'm going to go ahead and open up in my little 120 folder, I'll open up sort of what I did for session 3, or assignment 3, excuse me. I'll open up the one that sort of looks more like the plain version of it. This should hopefully give you a sense of like what one finished result might look like. Yours doesn't have to look just like this. So it sort of demonstrates the intent. Looks like it's doing a lot of flashing around as it generates all the different pieces. I'm just waiting for it to regenerate on this side. Actually, I think you can see pretty accurately like what I'm seeing on my screen right now. It's trying. There's an awful lot of different little planes in this one. There we go. So here's the idea of the basic structure. In some ways, you'll recognize the structure as being very much like the parametric stadium, even with the panel that has the opening in it. But we've adapted it a little bit just so you get a sense of how this can work. Okay, let me see if it stops opening. I'll spin this around. We'll take a look at this. So if I orbit this thing, you can see on that side it actually looks very much like the parametric stadium we've been working with in the past. On the front side, though, it looks a little bit different. Let's talk about that. What we've actually done is say that as opposed to just using 4 different lines, or 5, depending upon whether you want to kind of control the inside of the truss. Let me zoom on in and I'll show you what I mean by that. It stops regenerating here. I definitely need to open smaller examples when we're working online here like this. Okay. See if I can zoom on in here a little bit. Okay, so the idea is typically this truss is really defined by its 4 different points. There's actually 2 different versions of it. There's a 4-point version, a 5-point version, where for each of the different trusses, you'll see it has placement points down here at the bottom. Number 2 is kind of what I'll call the back corner. Number 3 is kind of the top, and number 4 is the end of the truss. Okay, the end of the overhang. And that kind of is generally okay. There's actually a 5-point version that you might want to work with instead. The 5th point is actually this point right here in the middle. Let me see if you can see my little mouse moving around there a little bit. It's right there in the middle. It's that interior point of the truss. And if you don't control that, that just sort of ends up in the middle. If you do control that, you get a lot of kind of control over exactly where that ends up if you want to customize the truss some more. But here's what we're asking you to do is go ahead and kind of make long linear lines for those 4 or 5 points, but then do something just a little bit different. For that 4th point right here, don't just kind of let it be a linear point. Okay, actually allow that you could change that by introducing some sort of a wave function to it. And what I've done here is actually introduced a little bit of a sine wave. So if you look between, this point right here, okay, which is the 2nd truss point, and this point right here, which is the end of the 1st truss, you'll see there's actually a little sine wave in the panels that's continuing there. And to do that, what we've done is just taken like a line 4, and instead of saying that it's a linear series between there, we've just changed the y value. Okay, so that's what we really have in mind, is just do something that gives you a little bit of variation in it, and just kind of experiment, sort of see if you can kind of come up with something that's interesting. You know, you can have a lot of fun with the sign value in terms of, what the amplitude is, of how big you want to go through and have that either extend up or extend down. You can also play around with the frequency. If you sort of match the frequency to the truss spacing, then you can have the sine wave end at even increments. In this case, what you're seeing is actually a whole cycle being completed between the two different truss points. So the whole frequency is equal to like the spacing between the different trusses. Okay, but again, kind of play around with that a little bit. You'll find examples of that in a lot of the stuff we've been working with in the past. So that's the first part of the assignment. Just go ahead and see if you can go through and create that. Let me see if I can get myself back over to the assignment, and we'll talk about the next little piece of it. The idea is, so create a wave at the end of the cantilever openings, panelize the surface, okay, and go ahead and do that using just the grids, creating the quads from the rectangular grids. Okay, I'm actually suggesting a special node for you, a special panel type called panel with solar panel option, and that's just sort of a slightly custom one we put together that we can use in terms of making the panel solar smart. Let me show you what the difference is on that, just so you know about it. The idea is we've been working with, this just panel with an opening in it, and that's fine. You can control that opening by putting in a value between 0 and 0.45, something like that. The idea of going through and making it a little bit different is I've actually sort of customized that panel a little bit, and this is one of the things that's available in that starting point file. Let's see if we can open this up. It doesn't flash too much. This panel is just a little bit different than the other one. It actually has a second piece to it. So what happened? Let me zoom on up so you can sort of see the adaptive panel. What you're used to seeing is this part underneath. There's a part that has the aperture in it. Let me kind of flip that over so you can see it. There you go. So that's the part that has the little aperture in it. You can see that there's the opening, and that's the part we have been working with in the past. This one's a little bit different. It actually has this other piece, which is supposed to indicate a solar panel up on top of it. And how we can actually control that is there's actually just an instance variable we set up to either make that form visible or make it invisible. And you'll find that it's just solar panel is the name of the variable. It's default, it's a checkbox, so it's yes or no. By default, it's set to off, but we can make it either true or false, depending upon what we want to show that. So the idea of how we can use that is as follows. Back over here, as you're placing the different panels, you have the option of either turning that on or turning that off as an instance variable. So the idea is in the same sense that we can use the idea of the directness of the sun to control the size of the opening, and we could also use it to sort of colorize the panels. We could also use that to set whether or not the solar panel will appear. So for example, in this panel right here, you see that solar panel's turned off right now. In this panel above it, it's actually turned on right now. And we're doing that just based on the directness value. So how direct this panel is oriented relative to the sun. So the whole idea, what we're suggesting in the assignment to do, a little too far, is go through and based on the adaptive or the directness value, go ahead and just sort of turn that on, either true or false. So you're going to just be setting an instance parameter of the panels just based on a threshold. In this case, I was suggesting 0.8. So if it was over 0.8, say that that's actually a very prime panel that we might want to put a solar panel on. If it's less than 0.8, say that, hey, that's not really so prime, so maybe we'll save our money and not put a panel there because it won't do us as much good in terms of being directly oriented to the sun. So that's really the idea behind what we have in mind. In terms of extra for experts, there's a couple of different things that you might want to try there. Again, these are things that you can do for bonus points if you're feeling adventurous, but you're not required to do these. This kind of depends on how easy the rest of the assignment was for you. You might want to go ahead and try this. Over in that airport example, let me kind of pop back over there. Hang on just a second, see if I can get that back. A little too far. You'll see that here I've actually loaded in a series of different panels on the front of the concourse too. The idea is if it was a big airport concourse, we might want to enclose that with some glazed panels. And we did that in a very straightforward way. It's really just kind of taking, again, a panel element. In this case, it's a big glazed panel with a little bit of framing on it. And we've included that. There's an example of a panel you can use, again, in that assignment 3 starting point. But really what we're doing is just taking a new line with equally spaced points down along the base, and we're just really bringing at the upper points of the quads, we're just really using that same line 4, which is determining the shape of really the end of the roof. So just bringing those together and creating a bunch of different panel elements. So that's really the idea behind the assignment. I just would rather let you sort of dig in and sort of like start thinking about it and asking questions. And you can do that like during that little break between say 10 and 10:30 when we have a chance for you to kind of explore that a little bit. And then I get back together again like at 10:30 to continue. But like let me just kind of pause there, see if there's any sort of general questions about the assignment or if that's all sort of straightforward enough and you're just ready to get going. So anyone either online or in the room, if do we need to explain that any further, or you're ready just to kind of dig in and see what questions arise? Okay, sounds very good. So go ahead and have at that. See if you can get yourself started during that little break we're going to have at 10 o'clock. Let me go ahead and put that away for a second. I'm also going to go through and just close this window because, oh, yeah, when Revit's being so slow with all these windows open, or actually it's just, really what it is, it's just this complex surface that's open. Let me close that window. It'll really speed things up and hopefully do a lot less just flashing around in GoToMeeting. Okay, let's see, finish closing up. It's just working hard. We're going to go back to a simpler example that has a whole lot less panels on it and work with that. Here's that little rectangular grid, glazed frame panel. Let me close that thing up. So you know there, that was the solar panel. Again, we'll get back to this Revit. Okay, so here's what we're going to do. We are going to return to the notion of optimization and really look at this whole idea of finding highs and lows and controlling the finding of highs and lows, and just look at a couple different examples of how we can do that. So let me flip on over to, not that, but just sort of the assignment description or the session description about what we're up to today, and give you the overall sense. So we looked at last time the whole issue of really driving different values and kind of just testing a bunch of different values and ultimately pulling values back out of the model. And the idea was that when we were going through and computing something that wasn't just sort of a simple formula, but could actually involve just something of, hang on a second, I'm checking a comment here. Sounds good. Okay, something that actually involved using the Revit model to figure out the value. That there was a way of kind of just recursing or just working through all the different values, testing it, and getting the values out of Revit, collecting those values as a test. Okay, then the next step is really to go through and really figure out where the highs and the lows are. And we're going to start with sort of just a very simple one, just to kind of walk through the basic script for doing that. I kind of did this really quickly at the end of the last time, but let's kind of do it a little bit more slowly this time. Then we'll generalize it a little bit so that we can do it to sort of any parameter that we want to pull out and optimize, including some parameters that we can kind of be computing on the fly. So the idea was that after we went through and tested the basic values, there were a couple different steps to really figure out the highs and the lows. And those looked like this. We wanted to go through and take the values that we were testing and actually just convert it into what I'll call a hierarchical list, because I know how to operate on lists as opposed to text strings. Okay, based on those lists, we were going to go through and just pull different values out. Okay, so we were going to pull out the two different columns of things that were in the list, the things that were in the result list as the test values, and also the ones that are the list of the results that came from the testing. Okay, and the way we're going to do that is in our little hierarchical list, column 0 is going to be the things that we were testing, and column 1 we're going to be the things that are the results. Then out of that, just go through and sort that list based on the results, and then just kind of pull the high and lows and ultimately set the values of the Revit model to match those highs and lows. So that was kind of the overall script, the overall form of what we were up to. So let's go ahead and take a look at that over here in Revit land and just kind of see what the scripting looks like and really kind of unpack it in more detail. So the idea over here is if you go to, in session 12, let's open 12.1. We again are working with a very straightforward, just rectangular box. Okay, that's a good starting point. That gets us going. But in that rectangular box, what we're going to be doing is looking at just the gross volume of the box. That's one of the parameters we can pick out. We can pick out a number of different areas, or volume, or parameters out of the box. But let's talk. We'll do the gross volume first, and then we'll generalize from there. Still just a lot of flashing in Revit. Give it a second to catch up with us. There we go. It's our simple box. Not very interesting in this game. But let's go ahead and choose the box. You'll see it has some instance parameters. It has like height, width, depth. And it also has like a gross surface area, gross volume, a gross floor area. The floor area, you notice, isn't actually filled out just yet. And the reason there's no floor area to it just yet is we haven't actually divided this thing up into mass floors. If we did divide this up into mass floors, that would be available to us too. And we'll do that in a little while, but let me just kind of show you. The general principle is that if I have some levels defined, as we've done in the past, and I say mass floors, I can choose the different floor levels that I have available. And I should add more floor levels. But based on those two different floor levels, you'll see there actually is a gross floor area right now. It's a small one right now because we've only allowed floors at level 1 and level 2. But there's different variables, and we can compute other values that relate these things together too. But we'll keep it simple. At first, we're just going to take a look at this, the gross volume, and just finding the max for the values we're putting in there. So if I go to Dynamo, let's just go through and take a look at the scripting that drives that. I'll go back into the add-in, and if you open up the 12.1 script, we'll see if we can do that. In the background, looks like it's trying to open. Okay, let's just take a look at this basic logic. looks like that still actually is the older logic. Hang on, let me go back over here. That looks like the logic from my airplane example. So that's not what I want to get for you right now. Hang on, let me switch that back out. It's fine with Dynamo. If you, actually what I'm fighting is just with the screen refresh on Revit. Can you stop? Let's see if I can close that window and get it to stop doing what it's doing. It's like it's almost caught up in like some bad loop in there. Okay. Close that one. Let's see if I can bring it up again. Okay, here we have the plain Dynamo environment. Let's just going to open up the 12.1 and we'll go from there. Because the scripting in here is actually not all that difficult, but there's just sort of these like slightly new constructs that we've been working with. And let me open this one. You'll see that I also have loaded a series of different custom nodes that we use as part of this whole script into the same folder. It's important that those custom nodes be there so they can be found at the time you open things. If you open the script and those custom nodes aren't there, those nodes will show up in red. It won't be able, or it'll show up kind of hollow. You won't really know what to do with those. So the easiest thing is actually just to sort of put the nodes in the folder and reopen things. You might have to kind of just restart Dynamo to get it to do it. But let's take a look at really what the logic behind this is. What we wanted to do is basically just go through and take the box. So we start with the family of the box. We're testing the height. Okay, that's the value to test or value to change. We're going to go ahead and report on the gross volume being one of the different variables, one of the instance variables that's reported back out. We're going to write temporarily to this little file write test. And I have just a range of values. So this is kind of stepping across an entire range using 4H. It's not really using recursion, but it's just kind of moving between 20 to, let me kind of ratchet it down a little bit. So like 80 or something like that. And you can choose an increment, whether you want to do it by 10 or you want to do it by 5, whatever it is. It's going to test, so this will test 20, 25, 30, all the way up to, it'll test up to 85. It won't go ahead and test 90 though, because that crosses the threshold. So out of that, what it's going to do is basically go through and just return a whole bunch of different values. It's going to apply this function for each to each of the values, 20, 25, all the way up to 85. It's going to basically perform these steps, first writing the file, then evaluating, then reading the text file back in. So up to this point, right about here, okay, it's just basically creating a string. Actually, I take that back. Creating a file in the CSV format, because we're writing it out so that it is value, comma, value, and putting carriage returns in between. So let's just go ahead and take this over in the background. Let's just kind of run that. And we'll just take a look at how it runs. So it's going to start at 20. Go get the value for 20. You can go through 25. Go for 30. And it's going to just kind of march its way all the way up there, all the way up to 80. As it's doing it, it's going to be grabbing this value gross volume down there. And I'll admit, the gross volume is not all that interesting because the gross volume relative to the height for this simple box is a fairly easy thing for us to, we could have computed that. We don't need the power of Dynamo and all this kind of optimization to do that. But we'll go ahead and make that a lot more complicated in just a few minutes, or give us something that has a lot more value in it. So let's just let it go through these different values. If you can, please go ahead and run this along on your machine so you're looking at the same thing, because then you could actually do the same sort of watching of the different node values and test it as we're working. Okay, up to 60, so I should get like 4 more values here. 65, 70. It's amazing to me how slow things are running in this environment. I think something has to do with GoToMeeting as well as I'm recording this in QuickTime all at the same time. And it really just slows down Revit tremendously. Okay, there's 80. And hopefully, at the end of 80, we should be done. Nope, 85. I take that back. There was one more. I'm waiting for the little run button to appear again to indicate that it's done doing what it's doing. The tail end of this script does a couple of different things. It finds where the largest, or we could be finding the smallest gross volume is, and then it sets the value of the box over there to actually match that highest or lowest value. So let's take a look and see if we can make that make sense. Okay, so here, let me zoom on in. We could do this by watching, or just kind of hovering over here. You'll see this is the values. This is just being written out as a CSV string, 20, 25, 30, and each of the different volume values. Notice there's that little bit of error, and that has to do with this whole conversion between meters and feet we talked about last time. I'll live with that because it's not going to substantively change the value, but it'd be great to kind of get that a little bit better. What I'm doing here is basically just converting that CSV text to a hierarchical list. Okay, that's going to give me a list where I'm just breaking all those different lines that have the comments into them into a list of lists. So each list item will have 20, it'll have the test value and the result, okay, and there's a big list of all those together. This whole notion of the Boolean over here, that just really has to do with whether there is a header string. So over here, I actually do have a string that just sort of says what is in the file. All I'm doing is by indicating there's a header string is just stripping that off so that when I look at the list of values, I don't actually consider that. Okay, and I encourage you, and I won't do it right now, but go ahead and take a look at the right CSV text to hierarchical list file, or the custom node. Look at the programming logic behind it. It's actually pretty straightforward. It just breaks things down first by carriage returns and then breaks them down item 1 versus item 2 based on being on which, either before or after the comma. So it's a good little custom node, one that you're going to get a lot of information from. Okay, next up, after we go through and grab all those different values, here's what we want to do. We want to go through and get all the values in column 0 or get all the values in column 1, okay, and based on those values, go ahead and return them. Okay, so let's talk about how we do that. Here's the different values. There's column 0 and column 1 right there. It actually did pull them out, but let's talk about what you have to do. It turns out to get all the values from them and return all the values, it actually is very helpful to use this map function. And let me talk about that map function, because the map function is incredibly useful to you. You might remember the map function is very much like the for each function. Back over here, we used a for each, which took a range of values, plugged it into the test value of this function, and just basically performed that on every individual step. Map is amazingly similar. Map actually says not only plug the values in, but return a list of values. So each of these different little custom nodes get return lists for custom column values. Let me just kind of show you what it looks like. Just says, give me the index, the column you want to get, either 0 or 1. Give me the list that you're feeding me, and then get from list. But what I actually have to do is actually map that list and the function get from list to actually get that list of values back. I know that seems a little strange. It'll take like 2 or 3 times for you to sort of like do it and realize when you actually need to use the map function versus not. But the telltale sign is generally when you try to go through and apply a function to a list of values and it complains, it says, hey, I can't do that on a list. Okay, I can do that with a bunch of values, but I can't do that for the list. When you're getting that kind of message, that's your clue that, oh, I need to use the map function to apply this to the list. And what it'll do is then, take that list and basically all it's doing is getting the items from the list one at a time. But let me pause there for just a second, because I know map is kind of a strange concept, but let's sort of see if that makes sense to people. Does anyone have any questions on map? It's like one of those really useful things. No? Okay. If you are good on map, let's just kind of talk about the tail end of this. What I wanted to do is actually just get the extreme values, like from the list. So what I wanted to do is basically just get all those different result values, that same list that you're seeing over here, and just sort the list based on those. So again, we could have done this just directly in the logic of the main node or the main diagram, or we could go through and put this into this custom node. And I chose to put it in a custom node just because I thought that would be a useful function to use in a lot of different places. Oops, hang on. Let's see what's going on here. Okay, sounds good. So in this custom node, all we're really doing is, again, getting all those items from the list by mapping it. But then I'm taking that list of values and I'm basically, let me pull that out over here. Okay, I'm sorting the list based on that function. So I'm sorting it based on the values that it's pulling from column 1 or the test results. Okay, so I take a list, I try to apply a function to the list to sort of pull out a specific value, and I'm sorting by that because I'm treating those as the key. Once I have those values, okay, I can go through and either pull the first of the list or the last of the list. Let me put a little watch in here so you can sort of see what it looks like. Custom nodes are kind of bad in that you can't just preview. You have to do some watching. Now I'm going to have to run that again to do that. I won't do that because it'll take the time. But it'll basically sort out things by all the different test values. And I'm just going for the first of the list and the last of the list. The first being the minimum values, the last being the maximum values, and just getting things from the list. By getting things from the list, getting column 0 is getting the test value, getting column 1 is getting the return value. So it does that for both the high and the low. Then we'll go through and do sort of a similar thing over here. After we get those values, I'm just setting the final value of the box to actually match either the high or low. In this case, I'm setting it based on the high value that we're testing. So I'm just setting the parameter. In this case, it's the parameter height, and I'm setting it to match the maximum value, which is why the box over here in blue is showing up the maximum height. Okay, let's just pause there for just a second, see if that kind of makes sense. Because the next thing we're going to do is actually just a really simple extension. Once we have a way of finding a high and a low, it really just gets down to sort of what sort of variables we want to pull out and what we can define to go through and pull out. So if you can handle getting highs and lows, then it's just a matter of saying, super, which variable or which instance parameter do we want to check on something? And if we need to set up a formula to compute a different instance parameter, we can. Okay, any questions? Or are we feeling pretty good? Super then. Okay, let me go ahead. I'm going to open a slightly different example and close that up. Because just getting the volume based on the height of the box, that's not so interesting. Let's talk about a slightly different example. And that would be, let me close this one up. If I go to 12.2, okay, let's open that one up. .2 just is taking the same basic idea, but just doing something that's a little more interesting in terms of the calculation. So let me open that one up. In this case, I've taken the little box object and I've just added a few variables to it. I've added a few more parameters to it. Because the box always reports the gross area, it reports the gross volume, it will report the floor area if I had mass floors. Okay, but we can start trying to relate some different things together. Okay, let's see what's going on here. Okay, looking good there. Let's let that open up. What I did with this box, hopefully yours is open already. Let's go ahead and take a look at it. See if you can choose the box and say edit the family. We'll take a look at some just formulas I set up within the side of the box just to make it a little more interesting. Okay, so here's my box. I'm going to just choose it and I'll edit it. What I want to do is create a couple more variables for me to work with, a couple more parameters that I could work with. So I started just setting up some relationships between the different values, in that family. So one thing I was interested in was this whole notion of, if we were trying to maintain a total amount of area in the building, if we wanted a total amount of gross square footage, that we get in the building, and we want to play around with different sizes and shapes and parameters and things like that, how we could actually sort of make that work. So for example, let me open up the parameters that we had available here. I started with the whole notion of, we had the variables width, height, and depth. But I wanted to say, like, what if we actually went through and, just had some notion of a target floor area that I wanted to create 100,000 square feet or something like that. That how can we sort of relate all these different variables together? Okay, and there were a couple different ways we could approach that. Actually, let me even remove this one because that's not really doing anything for me. Let me remove that line. Okay, there was this whole notion of really how many different floors we could have on the building based on the height. So for example, what I did here was I had a floor-to-floor height of 10, and based on the height, let's say for example the height was 30, you see I get 3 floors out of that. I'm just rounding down the height divided by the floor-to-floor height. And then based on that, we could say how much area do I need per floor? So I'm taking that basic notion of, if I have the 3 floors, 100,000, I'm going to require 33,000 square feet per floor. And again, that would change. If it was 200,000, it'd be 66,000 square feet. I'm just sort of basically relating some things together here. Okay, now as we are working, we can actually go through and just sort of, start changing things around a little bit in terms of making this all work. So for example, the target floor area was a certain amount, if I wanted perfectly square floors, what I could do is just take the square root of that, okay, and say that the depth is the area needed per floor, the width is just the same thing as the depth. Okay, that just makes perfectly square floors. So given a target floor area, can I just break it in the square root? Let's go ahead and change it around a little bit though, make it a little more interesting. What if we knew, for example, that we wanted the width to be, let me even go ahead and put in a value in here. Let's say that the width wanted to be, we knew it was going to be 100 feet. Okay. The depth at that point could be equal to the area needed per floor divided by the width. Okay, and that'll just sort of set up a relationship. We can now go through and go through and optimize based on in this case, what did I optimize this time? I think I optimized based on what's the floor area? That's the volume. Let's go ahead and take a look at it. Okay, so I basically set up a relationship here where I have a relationship between width and height as opposed to being square. Now I'm going to go through and make it 100 foot even. I could do something else. For example, I could say that I want them to have a 2-to-1 relationship. Okay, so 2 times 1 times another of that. So what would I need to do? I would basically need to divided by 3. That would be another way to do it. I have to think if I'm doing it right. There, times 2. Yeah. Well, I'll do it this way first. I don't want to get caught up in the math because I'll make some mistake and I got to think about whether there's going to be a squaring in there or not. But you can take the idea that basically you want to introduce the 2-to-1 relationship and just adjust these 2 different formulas to keep it constant. Okay, let's say okay to that. So there's a relationship between these two if it always has to be 100 high or 100 deep, excuse me. Let me load that into the project. It'll load in some initial values, hopefully. It's still updating. Okay, so based upon a target floor area, that's interesting. Hang on just a second here. I think it's still updating. It's funny, it hasn't reapplied itself. Let me make it 150,000 square feet. Okay, looks like it's okay up here. It just hasn't sort of really rearranged itself in here just yet. Okay, let's go ahead and take a look at this. The idea is now, if we go through and run Dynamo and do some optimization, we can switch on over to a slightly different script. Let me open this up. Okay, we'll open up the script. You see, this one is very, very similar to what we did last time. I still have this box with the target floor area. In this case, I'm going to choose the parameter to report. Okay, in this case, I'm going to go for the report area. Let's go ahead and take a look at that. Oh, that's just a type of parameter, excuse me. It is gross surface area. That report type parameter, that was just used for the little scaling out factor, but I'm going to use the gross surface area as the value I'm pulling out. Back over here, after we run the test, we pull this all out. And what I'm going to do is basically just find the value that has, what is it, the minimum surface area. Again, the idea here is that we want to go through and find the volume shape, the one that'll have that volume, but actually have the minimum amount of total gross surface area. Okay, so if I can run that, it'll run through all the different elements. In this case, it'll be a slightly different size. We'll see what it'll do, because we sort of inherently have put a constraint on it that it has to be 100 wide. We'll see what it comes up with. That's what it thinks is the optimum area, or the optimum height, to kind of really give us the least amount of gross surface area. Again, just computing all those gross surface area values. Okay, just running through all different values. So again, what this is going to try and do, what we've set it up to do here, is try to optimize the minimum amount of surface area. The idea is that's often a very good thing to do relative to the notion of just energy efficiency, because the less amount of surface area we have interacting with the outside environment, typically the better the energy performance. You always want to try and get as much volume as you can with as little surface area as possible. So holding the volume constant, just minimizing the surface area, tends to be a pretty good thing to do. Okay, it looks like it's just about done. Nope, maybe I ran it all the way up to 200 feet. So 190 and finally coming to 200. Great. Okay, so we have some different values here for the gross surface area. You can see when the box is very squatty, okay, it has about 184,000 square feet. It looks like it gets sort of smallest right here in the middle somewhere, right around values 11 or 12, somewhere right in there. Okay, it's like 120 or 130. You can see it's actually chosen it over here. Yeah, 120 as being the minimum value. It looks like that the minimum value is right at 120, and the surface area at that point is 79,000 square feet. So let's go ahead and take a look at that. That probably will make some sort of intuitive sense to us relative to the shape of the building. Okay, still relatively cubic in the scheme of things, which is often sort of a good looking form. So it's kind of doing about what we expect, which is kind of good. So let us do this. We're going to go ahead and break right now, but how about this as we kind of use this next half hour when I have to be away, but to go ahead and actually do something where you can. Go ahead and take your break for about 5 to 10 minutes, but let's do this when you come back. Either jump into assignment 3 and kind of play around with that, see if you have any questions about that. Or if you want to keep on going with the whole option of the optimization, why don't you go through and try this? See if you can, over here in the family itself, okay, see if you can actually create your own sort of parameter to indicate an area, but as opposed to the gross surface area, let's look at it a little bit differently. What if we were looking at kind of a weighted average area where we looked at the wall surfaces, okay, as being, having a weighted factor on them. So all the area of the different walls has a factor of, say, maybe like 2 to apply to it. The roof surface has an area of like a weighting factor of like 1 applied to it. And the ground surface actually has a weighting factor of 0 applied to it. And what that starts to get to is often when we're doing buildings and you think about the insulative or the conductive values through each of those different surfaces, the roofs are often very heavily insulated, the walls are less insulated, the floor or the ground surface is often considered to be perfectly insulated. So by putting those different sort of weighting factors in there, what we're going to do is start doing a better job of reflecting the thermal conductance conditions as opposed to looking at gross floor area. So again, the idea would be to go through and define some new formulas over here that based on the height, width, and depth, we'll go through and do that. It'll give you sort of the wall area, applying a weighting factor of 2, the roof area, applying a weighting factor of 1, and the ground floor area, applying a weighting factor of 0. Add those 3 things together to get what we can call like the weighted average area, something like that, and then we'll optimize based on that. Okay, so if you can do that, well, over this next half hour, that'd be fantastic. And I will join you all again probably right around 10:35. Okay? So let's go ahead and take our break, and we will be right back.